Hello, everyone, and welcome to today's webinar implementing MLDSA and LMS to secure the future of software code signing. I'm Surbhi Singh, Senior Consultant at Encryption Consulting, and I'm glad you could join us. Today's session will explore how post quantum algorithms like MLDSA and LMS can help modernize your software signing strategy and protect critical assets against future cryptographic threats. Leading the session is Riley Dickens, Senior Consultant at Encryption Consulting, who will walk you through the practical implementation steps, hybrid signing workflows, and integration strategies. Feel free to drop in your questions in the Q&A bar below and we'll address them at the end. With that, I'll hand it over to Riley.
Hello, everyone, and welcome to another webinar with Encryption Consulting. My name is Riley Dickens, and I'm a senior consultant at Encryption Consulting, as well as lead software developer on our product, CodeSign Secure, our code signing platform. Now, today we're going to be diving into MLDSA and LMS and how you can use these post-quantum cryptography algorithms to secure your code signing and software signing future. Now, there's a lot to get into with this, and we'll first start off with an introduction to post-quantum cryptography. Now, this will give you a good insight into what PQC is and how it works, and how MLDSA and LMS fit into this. Next, we'll talk about how MLDSA and LMS work, as well as just understanding them at a theoretical level. There's a lot of math that goes into these algorithms, so I'll try to stay away from that and give a more higher level overview when we discuss MLDSA and LMS. After that, we'll talk about the deployment workflow and just understanding how to deploy LMS and MLDSA within your organization for code signing. Then we'll talk a bit about best practices for integration. And finally, we'll just take a quick look at CodeSign Secure and what we offer in terms of MLDSA and LMS, as well as I'll give a quick demo on how that works. So, starting off, let's talk about post-quantum cryptography. Now, many of you may already know this, but the computers we use today are considered classical computers, and any encryption we utilize, such as SHA algorithms or things like that, those are considered classical cryptography. Now, this is important because as time is going on, we're discovering more and more uses for something called a quantum computer. And this is a computer that works much more efficiently and much faster at doing things like breaking encryption. So with a classical computer, to break a classical encryption or classical cryptography, the time it would take a classical computer to do that would be several years, right? But with a quantum computer, classical cryptography could be cracked within minutes or hours. So as you can see, quantum computers cause a huge issue. It's something that's coming up very fast, and we have to be prepared to defend against it. Now, not only are quantum threats a need for PQC, but there's also this idea of data confidentiality. Like I said, classical cryptography could be broken very quickly in minutes, if not hours, with quantum computers. And that means that any data that is stored confidentially and that is protected with classical cryptography is going to run into a ton of issues. So making sure that we can still protect that data before quantum computers become a real viable device is very important. Now, going along with that is these future-proof standards. The NIST, or the National Institute of Science and Technology, releases a number of standards and regulations that are followed across multiple organizations and should be followed by the majority of cybersecurity teams. So making sure that we're ahead of the curve and we're using things like post-quantum cryptography in these standards is very important. So NIST has really prioritized making sure that we get these algorithms standardized and making sure that they are quantum resistant as well. Now, there are several different types of PQC. The two main ones we'll talk about will first be lattice-based cryptography. Now, lattice-based cryptography is built around these hard geometric problems like SVP, and it offers fast quantum-safe algorithms, which are ideal for software and firmware signing like MLDSA. So MLDSA itself is utilizing lattice-based cryptography. Now, going along with that is hash-based cryptography. This gives you a quantum-resistant solution that relies solely on secure hashes. So as quantum computers advance, so will algorithms and hash algorithms, I should say. And so in that case, will these hash-based cryptography algorithms advance? Now, one more I'll just touch on a little bit, even though it's not super related to what we're talking about today, is code-based cryptography. Now, this deals with providing resilience through these multivariate schemes, and it uses polynomials over a finite field. So just to kind of high level view of these different cryptographic algorithms and these different types of PQC, it uses a lot of complex math that would be much harder for certainly a classical computer, but almost definitely a quantum computer to crack. So these post-quantum cryptography algorithms will end up being a lot stronger against these quantum computers. Now, just a few notes to take in here. Gartner has released a report that they expect by 2029, quantum computers can break most asymmetric cryptography. So, like I mentioned, it's coming up a lot faster than a lot of people might assume, even though a quantum computer might seem like something out of a sci-fi book. Now, two other notes to make. There's been a lot of research and a lot of different estimates into losses that could come from quantum cryptography hacks and things like that. And the Hudson Institute itself has suggested that there will most likely be trillions of dollars worth of issues, especially surrounding things like Bitcoin, where if Bitcoin were to be attacked by a quantum computer and they were to successfully get in, then about $3 trillion worth of money would be lost. So it goes from current cybersecurity attacks that cost millions to costing trillions of dollars and some most likely bankrupting a lot of organizations just because quantum computers are around and the data isn't protected properly. Now, diving in a little bit into MLDSA and LMS, I'll start with a bit of a theoretical overview. So like I said, I'm going to try and keep it less mathematical, more theoretical here, and we'll just talk a little bit about these two algorithms and what they do. So MLDSA is referred to also as module lattice digital signature algorithm. So MLDSA it is short for, and basically this is a quantum resistant digital signature scheme, which is standardized by the NIST, and it uses that module lattice-based cryptography that we talked about. So basically it uses these extremely hardened mathematical problems to secure against even quantum computers. Now, like I mentioned, the NIST has standardized MLDSA, and that was back in 2024 with FIPS 204, one of their recent standards. Now, just a few notes about MLDSA. It is based on Crystal's dilithium, another algorithm, and so it is NIST vetted and found to be extremely quantum resistant. It has 3 different parameter sets. So if you think about SHA, you have SHA 256, SHA 384, and SHA 512. This is a very similar idea where these parameter sets are MLDSA 44, 65, and 87. Now, additionally, there's been a lot of talk of these powerful quantum algorithms like Shor's or Grover's algorithm. These have been found to crack a lot of classical cryptography, but luckily, we found that MLDSA itself is immune to these attacks with Shor's and Grover's algorithms. So it makes a lot more sense why the NIST has said this is extremely quantum resistant and it's good to use for the future to prepare yourself for quantum computers. Now, just taking a quick look here, we have our 3 different parameter sets. So as you can see, MLDSA 44 is NIST security level 2. It has different sizes for its public key, private key, and signatures. And it is considered the fastest of the 3 parameter sets. So this would be utilized in something like IoT devices, embedded systems with limited resources, things like that. Now, MLDSA 65 is a bit more secure at level 3. It's more of a moderate speed one. So it's in between MLDSA 44 and MLDSA 87. And it would tend to be used in places such as financial institutions or public sector applications, things like that, that still need a bit of speed, but are there a little bit longer and are a little more in place and structured as opposed to things like IoT devices or embedded systems. And then finally, we have MLDSA 87. Now, as you can see, there's a pretty significant jump here in the security level up to level 5. So it is the slowest of the three, but it is more than likely you'll see as you look at the key sizes as well as the signature sizes, the stronger one of these versions. So in organizations like governments or critical infrastructure, places that basically need long-term protection, you'll find MLDSA 87 being utilized a lot more. Now, jumping over to LMS. LMS, or Latent Michelai Signature Scheme, is another NIST-approved digital signature algorithm. This was approved and specified in SP 800-208 of the NIST standards. And again, it offers these very strong protections against quantum attacks. Now, this one, instead of being lattice-based, is more focused on the hardness of cryptographic hashes. So I talked a little bit about how as quantum computers develop and get better and better, so will hash algorithms. And in this case, that's great for LMS because as these hash algorithms or these hash functions get stronger and stronger, so will LMS as it can utilize these stronger hash functions. So that's one of the reasons it's so great for future proofing against quantum computer attacks. Now, a few notes I have here. The LMS itself utilizes these one-time signature keys. So these keys will all be used only once to sign, and from there they cannot be used again, and they won't be used again for new signatures. Now, these keys are arranged in something called a Merkle tree, and that Merkle tree itself allows many signatures to be verified by a single public key. So, going into it a little bit more, with LMS, it's a lot more suited to things like IoT, firmware, or embedded systems. And that's because it has a lot lower computational and memory requirements compared to MLDSA or some of the other post-quantum cryptographic algorithms that are running around right now. Now, like I mentioned, per that NIST SP 800-208, there are a number of different permutations or variants of LMS. And what it does is LMS itself takes in a number of different parameters, including the hash size, the node size, and the tree height. So if we take just a quick look at this, you can see if you have all the values the same, the hash function, that M or node size value, and you change the tree height itself, you'll have different identifiers. They'll look similar, but the parameter set itself is a bit different just based on what values you pick for these. Now, diving a bit deeper on these one-time security keys, they are only valid, like I mentioned, for one single signature. So that gives you a lot of strong forward security, which is great for things like LMS and future proofing for the future. Now, there's something going along with these one-time security keys called a LMOTS type code. And this defines the actual hash function, the security level, and the efficiency that are all used during both signing and verification. So if we went a bit more into the weeds here, you would see in the actual mathematics of, generating a signature, how those are utilized and what this type code actually is. Now, another thing I will note as well, when you are calculating things within LMS, you take into account N, which is the hash size, this W value, which is something called a Winternitz configuration, and a P value for the number of hash elements used in keys and signatures. Now, just taking a quick look at this, you can see as the W value, that Winternitz configuration, gets bigger, the P value, the number of hash elements, gets smaller. So that's one of the reasons this uses a little less computational memory and a little less just memory in general, because as you go higher with that W value, your actual hash elements using keys is reduced. Now, I know that's a lot to take in, and I know it was just a higher level view of LMS and MLDSA, but the main point to take away from this section, I would say, is why we need these algorithms. There's a number of different reasons. We talked a lot about these quantum computers and them becoming a threat sooner rather than later. So being prepared for that is very important. But there's also a few other reasons as well. And one of those big ones is standardization and identifiers. The sooner we can actually develop different identifiers and different standardization for these different algorithms, the better. And the reason for that is certain tools you'll find right now, like Sign Tool, aren't actually allowing you to use MLDSA or LMS because there's no strict identifiers. It hasn't been implemented in Sign Tool or things like that. And things like the IANA, which is utilized with PKIs and things like that, doesn't have OIDs or basically identifiers for these algorithms, so they can't be utilized in a lot of locations yet. So it's really important to make sure that that standardization and those identifiers are created sooner than later. Now, going along with this is, of course, certification and compliance. As time goes on, you'll find many of these different algorithms going through these different types of readiness for deployment in different organizations. And so they'll have to meet certain standards and compliance. So MLDSA itself is moving towards FIPS 140-3 accreditation, and LMS is working towards, or it already does, I should say, supporting HSM-based state management. So the general idea here is that they're moving through this process of being FIPS validated and things like that. And as of now, you can, luckily, utilize a hybrid method. So a hybrid method would be using something like PQC along with RSA so that the hybrids themselves maintain FIPS compliance as long as the classical signature is still valid. So you can utilize these hybrid signing schemes and things like that to ease your journey into PQC a little bit, as opposed to ripping all your classical cryptography out and replacing it all with post-quantum cryptography. Now, one last thing we'll talk about on needing these algorithms is adoption and security mandates. Of course, there will be a lot of different security mandates that come out that are required for organizations. And as time goes on, these PQC algorithms will become larger and larger in those. So using things like HSMs will require you to use MLDSA or LMS in likely the next 5 to 10 years. So it's really important that you stay on top of this and you're meeting your different directives, you're meeting your different standards, and just making sure that you're adopting things to get kind of ahead of the curve before all of this becomes commonplace. Now, we talked a little bit about theory here. Let's get a little more in depth on how they work. So starting off with MLDSA, there are 3 different structured phases to this. So there's our key generation, our signature creation, and our signature verification. And the same goes for LMS. Now, key generation itself with MLDSA starts with a random MLDSA seed that is generated to deterministically initiate the key generation process. Now, from this actual seed, the algorithm will take structured polynomials over lattices to construct a key pair. So long story short, a lot of complicated mathematics goes on within the algorithm, and the key pair is constructed. Now, if the generated values don't actually meet some certain predefined constraints, the process retries until it gets the correctness it's looking for. Then once the keys are serialized into a standard format, they'll be used for signature operations. So long story short, a lot of complicated mathematics goes on behind the scenes to generate our key pair. It is generated only once it meets certain predefined constraints. And once that's done, they're serialized, those keys, and they're ready for use. Now, in the signature generation field, there's this idea of a unique message representative, and that's created by actually hashing the message with random bytes. So far, sounds very similar to classical cryptography and creating a signature with classical cryptography algorithms. Now, from here, we separate the private key into component keys and actually regenerate the MLDSA key from the seed. So 2 component signatures are generated independently by signing that unique message representative and using their respective algorithms. So this is where things diverge a bit. It gets a bit more complicated in the signature generation once we're breaking up the key into component keys and actually generating these 2 component signatures independently of each other with their specific algorithms. After that, the final composite signature is encoded and output as a single value. Now, to actually verify that signature, We first ensure that the context length is within 255 bytes, or else an error will be returned. Then the public key and signature components are deserialized, and their format and type are checked for correctness. So a lot of correctness checking here in the actual signature verification step. Then the message representative is recreated or constructed by hashing the message with certain values like the prefix, the domain, the context, and certain randomness. And from there, we verify MLDSA and traditional signatures on that message, and the signature is valid only if both checks pass. So this kind of gives you a good idea of how a hybrid setup would work, something along those lines. Now, diving into LMS, again, we have our three essential stages, but it gets a bit different with LMS itself. So key generation itself, those LMS parameters like the hash size, the tree height, things like that are defined and set so that we can actually define the key structure and the security level. Then a unique ID is derived and generated, and all those one-time security keys, those private keys specifically, using the ID and the leaf indices are generated and derived as well. From there, we compute the one-time security key public keys and build a Merkle tree by hashing them pairwise up to the root. So again, without getting into details on Merkle trees and things like that, we generate our private keys, we generate the public key, and it all works from there going through that Merkle tree. Now, the LMS public key is the Merkle root. So it's the root with metadata, basically, of this tree. Now, while the private key itself is holding the ID, those one-time security keys, and a leaf index. So basically, you can think of it as a public key at the very base of the tree, the root, and then going off all the branches, those leaf indices, that's where our private keys lie within that Merkle tree. Now, for signature generation, we first use the next LMS one-time security key that is it's based on a Q value, which is the current leaf index. So say we start off at 0, then we move up and we move up. So once 1 is used to sign, we move that Q value up by 1 and we use the next key for signing. So that way we aren't reusing any of our keys. We then generate the actual signature using that one-time security key, using the selected private key. So the private key that we're at in that Q value, that leaf indices, and the message itself. From there, we construct the full LMS signature by appending it's called a Merkle authentication path for public key validation. So basically, it's some different values that are needed to actually verify that signature relating to the tree itself. After that, like I said, we increment that Q value so that we know where our next key is to be used for signing. And we securely store it so that we prevent any reuse of those one-time security keys. Now, for signature verification, first we recompute the one-time signature key, the public key, I should say, using the message, signature, and ID. So all those values are included in the signature. Using those, we can actually recreate the public key and assign that derived public key to the correct leaf in the LMS tree. So since we have that leaf index or those leaf indices, we know exactly which key was utilized for the signing. Now, using that along with the authentication path we talked about a moment ago, we can sequentially reconstruct that Merkle tree until we get to the final root hash for validation. From there, we verify our signature by checking if the computed root matches the public key root. So that way we can see that the root is matching our public key and things are as they're supposed to be, and that's considered a solid verification of the signature itself. So now that we've seen a bit more about MLDSA and LMS, let's talk about deployment. So diving into MLDSA deployment itself, there's a few different sections, and I first like to talk about prerequisites. So the Python SDK for MLDSA integration is necessary, along with HSM-enabled secure environment. So basically, so you can control key usage of MLDSA and LMS keys. We, of course, recommend, and it is necessary nowadays, to utilize an HSM within your environment that can actually handle these keys. And going along with that is making sure that your HSM has firmware and software that is compatible with MLDSA. So some HSMs right now do have them, some don't, but they're all slowly moving in that way so that you can utilize LMS and MLDSA keys within the HSM for signing as well as just for creating and storing them. Now, the next step of your deployment is key generation parameters. Now, key generation takes the key identifier, the key name as input parameters, and that allows you to label the key pair. So we have both a key identifier and a key name with MLDSA. Now, of course, depending on the level, whether that be 44, 65, or 87, that determines the key and signature sizes for our varying use cases. So thinking back to our table we discussed earlier, depending on what level of security we need or what level of speed we need, that will determine what the public, private, and signature key sizes will be. And then after that, within key generation parameters, we have our internal use of predefined lattice dimensions and noise sampling. Basically, it is this idea of using these different values depending on the security level that you need. So depending on if you've chosen 44, 65, or 87, that determines these predefined lattice dimensions and noise sampling that are tied to that security level. Now, one other thing to think about with MLDSA and deploying in your environment is implementation tools. Of course, like I said, using HSMs that can handle MLDSA keys, that can generate them, and that can generate signatures is very important for your MLDSA setup. Now, going along with that, of course, is automating signing with different scripts, enforcing randomness, and making sure that you have specific CMS or cryptographic message syntax attributes that are necessary. So kind of just making sure that you have some automation in place and making sure that your automation can handle things like MLDSA or LMS. And then, of course, using validation tools so that you can verify signature integrity, basically making sure that you have NIST-compliant MLDSA keys and that your signatures are valid after the signing occurs. So just making sure you have some type of new verification tool or an old verification tool that can actually handle MLDSA keys. Now, talking about LMS, again, we have our prerequisites first with our deployment considerations. And in this case, we're talking more about a Java environment with LMS supporting cryptographic libraries. So that's very specific to LMS, and less specific to LMS, which we already saw in MLDSA, is HSM usage. Of course, we always recommend, and like I said, it's necessary nowadays to utilize within your code signing deployments HSMs. So we're making sure we're using HSMs with the proper firmware, with the proper software, and that they can actually handle these LMS keys for key generation and signature generation. Now, key generation parameters wise, LMS needs a unique key name to identify that key pair. So whereas MLDSA has two different values to identify it, this only has a unique key name. Going along with that, it's important to note that with LMS, you generate a set of those one-time security keys that are equal to 2 to the power of h, where h is the height of the Merkle tree. So if we had, say, a height of 2 for our Merkle tree, we would need 4 different one-time security keys. Now, going along with this, of course, we're going to need to pick our M value, which is the hash length, and our winternitz width, which is that W value, so that we can balance signature size along with our performance here. Now, a little bit different that I'll talk about here with LMS is post-quantum SDKs or software development kit-based deployment. So you do need to set up Java and PQSDK so that you can configure it for LMS signatures. And performing signing operations within the HSM is another critical component of this. That's why I bring up these HSMs so often in here, is because you need to utilize these HSMs to protect the private keys, but also sign with those private keys. Now, of course, just a quick note here, higher tree height, that H value increases key capacity. So that is very important because you can have more keys relating to one public key, but it also requires more time and memory. So important to keep that in mind when selecting your tree height. Now let's talk about a few best practices for code signing integration with these PQC algorithms. So first up is adopting hybrid signing. Like I mentioned, you have the ability to utilize something like RSA and PQC, and you can have this hybrid signing in place so that your movement from classical cryptography over to PQC is very swift and very efficient as compared to rip out all your classical cryptography and plug in all this PQC. Now, next, as I've talked about over and over again, is securing keys with HSMs. It is always important in your integrations to have your HSMs protecting private keys and generating signatures with those private keys. Now, another big point that I brought up a little bit earlier was updating signing tools. So we talked about updating HSM firmware and software, but also ensuring your signing tools themselves support MLDSA and LMS with their current version is very vital. It's so important just because, making sure that your signing tools can actually utilize these is really important. So make sure you're keeping up to date with whatever signing tools you're using and keeping track of when they allow you to utilize LMS or MLDSA. Now, cryptographic agility is a very important part of any infrastructure, and now is as good a time as any, and honestly, a little bit better of a time since we are making this move into post-quantum cryptography to make sure you have a cryptographically agile environment. And what I mean by that is basically it has to be a flexible environment that can change as new algorithms come out. So if you can plan ahead, whether you're creating your infrastructure for the first time or you're making some changes to your infrastructure, just making it a little easier to swap out or upgrade your signature algorithms without making any major changes, it's very important to be able to do that within your infrastructure. Now, optimization of verification is a very big part of signing, of course. So having an updated verifier for MLDSA and MLS and using things like Merkle caching allows you to do things a little bit quicker, right? You can have faster LMS loads. You can have, faster information gathering basically from your tools. So it's very important to kind of optimize your verification as best you can. And then finally, testing. Testing is always such a vital part of anything. So making sure that you check your resource constraints, knowing how much storage you need, knowing how much RAM you need, knowing that you have it all to actually utilize MLDSA and LMS is very important. So upgrading that if you don't have that capability as of now is important, but just doing all these tests, especially within your environment, is very vital to making sure that you have a strong and well-functioning code signing system. Now, I'll just briefly talk about Code Sign Secure and some changes we made in the PQC space. So Code Sign Secure itself, with version 3.02, has introduced built-in support for post-quantum signature algorithms, so MLDSA and LMS specifically here. And this allows you to, of course, protect your code's integrity with the emerging threat of quantum computers. Now, we offer that ability for dual signature workflows. So whether you want to use classical algorithms or you want to use PQC algorithms, either is just as viable to use, and it makes it a little easier to transition into this PQC phase. Now, we also offer seamless CI/CD integration. So whether you want to use GitLab, Jenkins, Azure pipelines, or Azure DevOps, you can use any of those for your CI/CD pipeline needs, along with LMS or MLDSA signing. Now, of course, we always utilize HSMs, and specifically HSMs that can handle LMS and MLDSA keys, not only creating them, but also using them for signature generation. And we also align with the majority of all compliance standards. So any compliance standards you may need to meet, CodeSign Secure can meet them, and that includes in regards to LMS and MLDSA. Now here, I will give you a quick demo of MLDSA and LMS signing within CodeSign Secure. Just give me one moment. All right. So you can see here that we are in our CodeSign Secure portal. And under our Keys and Certificates tab on the left here, we have a drop-down menu, and we can do our classical signing where we generate a certificate, or we can generate a PQC key. So if I generate a quick PQC key, I will do an LMS key. So I will say demo LMS, and I'll set my width to 8 here. And I'll just leave these other values. But as you can see, we have a key alias, we have the hash we're using, and then the different values here that we would need to create these parameters. And that created our LMS key here, as you can see. And I will also create very quickly an MLDSA key. So demo MLDSA, copy that over. I tend to just use in this demo case the same plain name as the key identifier. And here we're just going to pick our faster MLDSA 44 as opposed to 65 or 87. And we'll create that. And we have both of our keys. Now, something important to note, LMS, of course, uses those one-time security keys. So we'll take note here that right now we have 32 remaining signatures. And once we do a signing, it should go down to 31. So we just tap our actions over here for LMS. We generate a signature. And with LMS, you're uploading a file to the server. So I'll just select my sample file and create that. And you should see in a moment here our signature, our detached signature has been placed in our downloads folder. And if I go to verify a signature here, I'll first provide the file, and then I will provide the signature we just got. So I'll run that through verification, and we should see a message of verification successful here. Now, same goes for MLDSA, except in this case, it is slightly different. So we'll generate a signature, and as opposed to a file, we're going to provide a hash, so a hash of the file itself. So I'll just send over that hash. We'll get our signature again. And then if I go back to verification, I again provide our hash here, and we actually upload the signature file as well. So if I verify that, we get our signature verified successfully. Now, if I just refresh my page quickly, we can also go into our new LMS key, and we can see the remaining signatures has gone from 32 to 31. So you're kept up to date on how many signatures are left with those LMS keys. So that's everything I have for you today. Thank you all for joining us, and I look forward to talking to you in our questions portion of this webinar.
Thank you, Riley. Now it's time to move to the Q&A portion of our webinar. We'll start to answer as many questions as we can live, but if we don't get to yours, please feel free to drop it in the Q&A bar below. Someone from our team will follow up with you directly after the session. Let's go ahead and take our first question. If quantum computers don't exist yet, why are companies already exploring post-quantum code signing?
So a lot of what we talked about, the reasoning behind that is just because we want to be prepared before they become an issue. So it's the same as setting up regular security for your organization. You always want to be prepared ahead of time before you actually get attacked. So that's why we do that same thing with quantum computers and things like that, preparing for that.
Okay, moving to the next question. Based on your experience, what are the biggest challenges organizations face when transitioning to post-quantum code signing?
So one of the biggest challenges that I tend to see is things like HSMs and signing tools and things like that need to be updated to actually meet, the different changes that come about. They need to be able to recognize MLDSA and LMS, and changing those out or updating them can become a really heavy task, especially if you have a lot of different tools you're utilizing in your organization.
Great. So the next question I see coming over here is, how do MLDSA and LMS compare in terms of performance and signature size when integrated into a large-scale code signing environment?
So I would say LMS itself is a bit more mature. It's been NIST approved for a little bit longer than MLDSA, and it tends to be already integrated into a lot of different products. So like I believe it's AWS KMS, and a few of the HSMs already utilize LMS. Um, MLDSA, on the other hand, is in the process of evolving and becoming a bit more widely used. But some of the problem does come from LMS being a little harder to manage, just because stateful it's a stateful algorithm, so it's a little harder to manage because it needs to make sure that it's not using basically the same key every time. It has to change the key for every signature.
So I see one more question coming up, which is HSMs only, not TPM.
So TPM are another method that you can use for sure. I'm not 100% sure on this question, what exactly is being asked, but with CodeSign Secure, we're just using HSMs right now, but you can definitely utilize TPM. Off the top of my head, I'm not exactly sure what, is already usable with LMS and things like that with in regards to TPMs. But it's definitely another option you can use to, store and utilize those keys later on.
Okay. So the last two questions that we would be taking up are, what are some of the challenges you've seen organizations face when transitioning from classical to hybrid or post-quantum code signing workflows, and how can they be mitigated?
So that's a great question. So a lot of what we see, and I'll just touch briefly on it, is dealing with that statefulness of LMS algorithm. It becomes a lot to track keys and make sure they haven't been used and things like that. That's a common one we see. We also see a lot where the signature size change from PQC or from classical to PQC is pretty significant. So having that extra space that you need to store those signatures, or making the package size of these signed products becomes very complicated and can cause a lot of issues that we see, or challenges for organizations switching over to PQC.
So the last question that we're taking up is, can MLDSA and LMS be used together in the same signing environment, or should organizations choose one over the other?
Mhm. I'm sure we'll see as time goes on, a lot of organizations basically picking which algorithm they're going to use based on use case. So we talked about, the different use cases that would be available for different algorithms and the speed at which they work. So it's really important for organizations to, decide based on what they're working with or what their use case is, which algorithm they're going to use.
Perfect. So these are all the questions that we'll be answering in today's session. If you have any more questions, or if you want to learn anything more about what we've covered today, feel free to reach out to us at info@encryptionconsulting.com, or you can visit our website. Thank you once again for joining us and spending your time with us. We truly appreciate it, and we hope to see you in the next session.